this video, you'll learn the basic steps for setting up a dynamic overset mesh case involving relative motions between mesh components. This demonstration is based on the airflow around the moving robotic arm operating in a clean room environment. The air enters the room at 0.1 meters per second through 3 openings in the ceiling, travels around the moving robotic arm, and then exits through 2 slits in the floor. As the robotic arm translates, its 5 components articulate relative to each other. I want to examine the effect of the robotic arm's motion on the flow of the air contaminated by particles of dirt that have accumulated on the room floor. I'll use a tracer to represent the concentration of dirty air which is originally at rest. I've loaded the background stationary hexahedral mesh describing the room geometry and appended the polyhedral mesh for the robotic arm foot, 3 arm segments, and the end effector. And here the meshes are overlaid. Each overset mesh consists of the robotic arm component wall and its surrounding region. Because the meshes of the last arm segment and the end effector intersect rather than overlap, I've used an auxiliary connecting mesh called a collar mesh that overlaps the spherical wrist of the end effector and the front wall of the arm segment. Here's what it looks like. I've enabled the pressure-based transient solver, energy equation, and standard K-epsilon turbulence model. For boundary conditions, I've set the inlet velocity to 0.1 meters per second and the outlet pressure to 0. I've also set the boundary conditions for all appended components to overset and defined the interface between the background mesh and all of the component zones. Now I can proceed to define dynamic mesh zones for robotic arm components that undergo rigid body motions. I'll enable dynamic mesh, clear the mesh methods, and create dynamic mesh zones. I'll begin by creating a dynamic mesh zone for the robotic arm foot, component 1, which will be moving as a rigid body. To control the motion of each dynamic mesh zone, I'll use a UDF that specifies the motions of robotic arm components. Here's a quick glimpse at the UDF code. The first function describes the transient motion of the center of gravity of component 1 in the x direction. The remaining functions describe the motions as simple rotations of the center of gravity for each robotic arm component around the local axis. Because I've already compiled and loaded the UDF, the motion profiles appear in the Motion UDF Profiles drop-down list. For center of gravity location and rigid body orientation, I'll keep the default 0 values. Component 2, which is the dynamic zone for the first arm segment, also undergoes rigid body motion. To specify that it moves along with the first component, I'll enable relative motion and confirm that the component 1 is selected as a relative zone. In addition, component 2 rotates about the z-axis in the local coordinate frame of component 1. For the profile, I'll select the function that specifies its rotation. Component 3, the cell zone for the second arm segment, follows along with component 2 as a rigid body. It inherits all motions from the preceding components, and it also rotates about the local y-axis. I'll select the profile function that defines its rotation and specify the origin of the rotation axis. Component 4, the cell zone for the third arm segment, moves along with component 3. Again, because relative motion is enabled, all of the preceding component motions are inherited by it. I'll select the profile that controls its rotations around the axis of this cylinder and specify the origin of its rotation axis. In its initial position, component 4 has a tilt of 45 degrees from its local y-axis. I'll specify the motion of component 5 representing the robotic arm end effector in a similar manner. It follows component 4 and its rotation about the local y-axis is defined by this function. It's also tilted 45 degrees from the local y-axis. Finally, I'll define the mesh zone for the fluid collar connecting component 4 and component 5. Note that similar to component 4, the fluid collar also moves relative to component 3. Other settings are also the same as for component 4. The setup of the dynamic overset meshes with relative mesh motion is now complete. When I initialize the flow, Fluent automatically establishes the connectivity between the overlapping meshes. Initializing the case will also provide a good initial guess. I'll skip the simulation process and show you my solution results. During the solution run, I generated 2 animations. My first animation shows the mesh motion on the ISO surface that intersects with the robotic arm components. You can see the changes in the mesh zone during the robot operation. The background hexahedral mesh is in gray, When different arm components move across the isosurfaces, you can see their overset meshes displayed in different colors and also the regions where the meshes overlap. The contours of pressure are plotted on the robotic arm walls. The second animation shows the path lines of the airflow from the room inlets to the outlets. Some air disturbances caused by the robot motion are clearly visible. The gray isosurface at the bottom of the room represents the updraft of the dirty air. Notice that the tracer isosurface remains stationary in regions distant from the arm's foot. The area around the foot of the robot shows small variations in the tracer isosurface. We can see that the contaminants remain below the robotic arm end effector throughout the entire cycle of the operation. This concludes this demonstration showing how to set up overset meshes that are subject to relative motion.